Hello and welcome to my class. I'm Grolin Annesley from ThinkMo Education. I'm currently a Cisco Technology lecturer. If you like my video, welcome to my study group. Or contact my teaching assistant. WhatsApp account is +6 5834444290. Today's topic is ARP and ICMP. Before starting the lecture, let me first talk about the use of the simulator. You need to install the EVE-NG emulator in advance, because it will be used later in the course. You can ask my teaching assistant to get the installation data package. There will also be a detailed installation tutorial for you later. Now the device virtual machine is already open. Let me talk about the simple usage process now. After today's get out of class, I will give you a simple experiment. So gotta get it installed today. After the virtual machine is turned on, the interface looks like this. When you open, before importing the image, entering the home page should look like this. Click Open Virtual Machine. Then import the image. The button above is On. Before turning on, first click on Edit. Here are a few caveats. Listen up everyone. After clicking Edit, the first thing to notice is that this network adapter. It is recommended that you choose NAT mode at the beginning. I emphasize, if you are familiar with virtual machines, then you can choose. But if you are new to virtual machines, then you can choose NAT. Wait a minute, I'll tell you why. Choose NAT here. Click here after choosing. Click here again. Finally click OK below. And then make a modification to it. Logically speaking, there will only be this one network card. You don't need to care about the following. This is what I used for bridging. The second thing to watch out for is the memory. The memory should be at least 2 GB in the CCNA stage. Can't be any smaller. Otherwise the device will not work. The third thing to note is that the processor. The number of processors can be changed at will. Usually the minimum is 2. Include the following 2 options. It is also recommended that you tick them. The first option must be checked. Otherwise, when we talk about the simulator, you will not be able to open the router and switch. Some devices may not support the second option. The computer I am using now, if ticked, it will give me error. If you can check both. OK. When you set it up, just click to start the virtual machine. This is its startup interface. This image will run after booting. When you see this interface, it means that it is booting normally. Will be slower. I just told you. You must use NAT. If some students choose a not NAT, this address is not available. Because wait a minute, when we do the experiment, to log into this address on the browser, and then on the page, that is, on the web interface, to perform experimental configuration operations. So you have to capture this address. Until this address appears. This is the first step. Second step. Now there is a prompt to log in. This is an Ubuntu system. We will not be doing any more operations under this system. Not available at this stage. It has a default username and password. The default username is called root. After you have entered, you will be prompted to enter a password. Password is Eve. Then enter the system. The configuration commands for this system. We don't need to do anything at this stage. The only one that everyone may use is power off. When you shut down, you can hit enter. It's off. But we usually shut down like this. Click here. Click to close the client. You don't need to move this interface. Just log in before doing the experiment every time. You don't need to log in either. Every time you do an experiment. Actually, as long as you can see this address appear, you are okay. You don't have to log in. This does not affect our experiment. This is the whole step. I look at the address just now. 192.168.191.128. Each of us may be different. This is mine. Yours may be different from mine. Wait a minute when you come in. There may be a login interface. There will be a username in the login interface. The username is admin. And the password is Eve. Then you can log in. After logging in, my current interface will appear. Let me show you. After entering the URL, it looks like this. Let's type it here. First is the username, admin. Then password, Eve. There is a native console below. After the emulator is installed, don't go directly to the web interface. You need to install this file first. Same. You can contact my TA to pick up this file. This is actually a patch for EveNG. It is a support class. It can be called a fool's installation. You just click Next. Then click Install to finish. After this is installed, let's go to this interface again. In order to choose Native Console here. Then log in. And then we're on a brand new page. If you have done some experiments before, you may find here are some of your previous experimental environments. If you haven't built an environment before, by default this is blank. First I turned it off. After coming in, the displayed interface will be like this. Logically speaking, left part is blank. Here are some of my previous experimental environments. So I put it here. Click New. Create a new experiment. You can enter a name here. For example, 123. Then click Save. Enter this interface. We can get started. We now explain how to add experiments. You can click on the left to add. But our common method is right-click. Add device. Here is a node. One click to add. Throughout the NA phase, we only use two devices. One is an IOL, routers and switches. The other is virtual PC. That is VPCS. This is a virtual PC. What we are using now are these two devices. After the emulator is installed, the mirror image inside is these things. The entire CCNA stage. All the way to the CCNP stage. In fact, these are enough. After you reach the IE stage in the future, there will be a new mirror. We don't use it very often now. Generally do NA and NP experiments. Both devices will use the corresponding. Let's take a look at this IOL first. That is routers and switches. After clicking in, let's look here first. This has an option. Here there are L2 and L3. L2 represents the switch. L3 stands for router. In this emulator, there is no layer 2 switch. All switches support layer 3 functions. So in the future if we talk about VLAN, we're going to emulate a switch. Just choose this L2. It is a layer 3 switch by default. But when we do layer 2 switching experiments in the future, use it too. As long as the third layer function is not enabled, it will be fine. So choose L2 is the switch. L3 is the router. After choosing Next, you can also select some corresponding icons here. It's all okay. For example, If you choose a layer 2 switch here, you can select the icon of the second layer exchange here. But we usually finish choosing the router. It defaults to the router icon. Here is the number of nodes added. For example, I'm going to put 2 routers now. Just type 2 here. Wait a moment and click Save below. After saving, 2 devices will come out. Look down. This has memory and flash. Don't worry about this. By default, we don't need to change it, because that's the amount it recommends. Further down is the interface. On the left, this is the Ethernet link. This one does not mean adding an interface to this device. It is a multiple of the default 4. If write 1 here, there are 4 interfaces on the device. If write 2 here, there are 8 interfaces on the device. On the right, this is the serial link. Then we also add 4 serial ports here. Just write it as 1. Then I want to ask you a question. If I fill in 2 here for the Ethernet link, fill in 1 here in the serial link. Wait a minute. How many interfaces will I see on the device? Okay. 12. There will be 12 interfaces on the device. The following do not need to be changed. Then we click Save. Now we can see both devices. These are 2 routers. So how do they connect to each other? Look. Click it. It will become highlighted in the form. Then left click and drag to the right here. I'll drag from right to left, because it's easier. Okay. This worked. Now it will prompt you. Select which interface of R1 to connect to which interface of R2. Below this is R1. Don't confuse its corresponding order. Above is R2. It is viewed according to the current pattern and order. So you have a choice here. Click on You can see. Now the Ethernet port below is 8. 4 as a set. 1 starts with 0. 1 starts with 1. The following 4 serial ports start with S. So there are a total of 12 interfaces on my device. R2 device is the same. Both are 0. Click Save. Save it later. It is equivalent to the successful establishment of this experiment. Now we're going to turn on the device. Drag a box with the left mouse button. Box, select this device. Right-click to open this device. It's turned on by default. After opening, it was gray just now. Lights up now. Then after booting. Now it's time to configure it. This is relatively simple. Just click it. Then there will be the connector that is now associated with the overall device. Sometimes, when everyone is linking here, it may go wrong. You may find, after clicking, nothing at all, or pop up a web page. Let me explain why. There is a setting here. There is an app. Then there is a telnet. Here you can choose what to use. I also installed the CRT. But I personally don't like CRT. I think that interface is too ugly. I usually use shell. If you are used to using CRT, change to CRT right here. Click here. Then when you boot up the device, the one that pops up is the CRT. So you can set it yourself after class. If something goes wrong, just take the time to contact my teaching assistant. Help you solve problems. Now I use such a connection software. Turn on this device. We are now really entered the system of the device. Okay. Let's start by saying some simple commands. We will officially enter some aspects of the equipment today. Slowly start to configure the device. When you get into a Cisco device, it will pop up an interface by default. You will be asked if you want to enter boot mode. The configuration wizard. Usually it's no here. What does configuration wizard mean? If you type yes, then it will ask you to change the hostname. With or without IP. Can't enter the interface. Etc. Something like this. But we usually don't use. This is an emulator. If it's real. When you type no, may ask you to enter a username and password. To log in. The default initial username of Cisco devices is Cisco. Password is Cisco. But the emulator doesn't need this login process. Some models of equipment need to be initial login with username and password. After that we will find an interface. Here is a router. Router is suffixed with a monitoring number. This mode is called user mode in Cisco. It is also the lowest level mode. Then usually we will not be in this mode. Overworked. Because its function is to only view a part of the parameters. It has fewer functions. So the future. If we want to check almost all the parameters of the equipment. Going to the next mode. Privileged mode. Type enable here. Optionally enter all names. Let me show you first. You see. Now the monitoring number becomes a hashtag. It is equivalent to me entering the second level mode. That is the privileged mode. But there is another way. A complementary method. If you want to enter the second mode, you don't need to finish typing enable. We finish typing N here. There are two ways. The first is to press the tab key directly. I can complete this enable. Then press enter. Can also enter the second mode. Press tab, it can auto-complete. If I type N here, I want to finish typing. But I can't remember the letter of the name behind. I can put a question mark here. It will prompt you here. Now all you can type is this command. Enable. So I can press tab here. No matter how many times you press it. It's this one. It's like it completes me. We're in another mode. In privileged mode. Can see any parameter. More than user mode. Although in this mode, we can view many parameters and configurations. But it still has a problem. It cannot be configured now. If configured, I need to go to the next mode. Called global mode. Configure terminal. Also called configuration mode. We enter such a command and press the enter key. So now everyone can see. Add a config after router. It means that you can perform more configurations in this mode. Actually, this is the most powerful mode. You can configure the routing protocol. Configure routing. Change some parameters. Do some strategy, etc. We can all do it in this mode. Further down there is one last pattern. This is very simple. Interface mode. For example, enter the interface configuration IP. Or change the mode. When entering the interface configuration VLAN, we call it the interface pattern. Please pay attention. We must first enter the global mode. Then enter the interface mode. Interface. For example, now this device is a 00 interface. I'm about to enter the 00 interface. Everyone will find. This becomes config if. It means that I am now in an interface mode. Let's summarize. And teach you how to quit. Now in overall interface mode. If you want to return to the configuration mode just now. That is the global mode. We have a command. Exit. Now you can exit. There is another way. For example, I am now entering the 00 interface. If I want to go straight back to privileged mode now, we can type end here. Certainly. There is a difference between the two. Exit is a step-by-step return. That is, from user mode to privileged mode. To global mode. Up to interface mode. Fall back from interface mode. Back step by step. If you want from any view. Return to privileged mode. Then you just type end. I also show you. For example, I am now entering the 00 interface. Except for this end. There is also a key called Ctrl-Z. After pressing Ctrl-Z, you'll also be back in privileged mode. You can choose these ways. So if we go back to this mode below, when going to exit, in theory, return to user mode. Let's hit enter and feel. You will find we are now in the initial mode as a whole. This is called really exiting the device. You're back in the user view. So here we can still come back. Here I will give you a simple popularization. We usually do experiments directly from user mode to privileged mode. You enter, enable, and you come in directly. But for many companies, for safety reasons, enter privileged mode in user view. There will be a verification. To enter password. It's like doing some defense here. If you don't know your device's passcode right now, then you have no way to log into the privileged mode. To view the parameters, let's see how it is configured. It needs to be configured in global mode. Let's receive the first command first. We first have an enable. Then enter a question mark to see. Today we talk about two modes. One is called password. The other is called secret. Let's first look at the password. We call it plain text. For example, I give it a password. Enter Cisco. And hit enter. It is equivalent to that I have configured the password now. Exit now. Back to this interface. Now type enable. After entering, it will prompt me to enter the password. Then I will now enter the Cisco we just said. Enter this interface. This is very simple. But it does not require everyone to master its commands. It's not difficult. Just feel it. May be new to such a system. It is actually an iOS system based on the Linux system. The difference between it and the Windows system is that the operating habits are quite different. So everyone sometimes doesn't quite adapt. Slowly get used to it. Okay. Let's check the current configuration. In Cisco, the viewing parameter is called Show. Click on the upper right corner. Select Settings. Click on General. Here is an app. What type of files do you open in the future? What kind of program do you want to open? Are set here. Let's look at the configuration now. The command now running on the device is running config. Running configuration. In fact, it is show run. Generally speaking, it will not be completed later. After typing this, we just press the enter key. Let's take a look. In this, we can clearly see a parameter. This is what we just configured. Enable password Cisco. We just entered this command in global mode. The password for the device is now Cisco. This thing is called plain text. Refers to when you view the configuration on the device. Can directly see the configured password. This password is in clear text. Okay. Let's look at another model next. The other is ciphertext. The ciphertext will not be able to see the password. So we go inside. To make a configuration. First, cancel the previous configuration. In Cisco, cancel the previous configuration is called no. What we just configured is enable password. So now enter no enable password here. To cancel the previous configuration, we are now going to reconfigure. To use ciphertext, still type Cisco. Press enter. Return to the original interface. Then log in again. It again prompts for password. Still enter the password to log in. After logging in, let's look at the configuration now. Show run. Everyone will find. Here we see the configuration just now. Enable secret. But there is a character after. 5. Prompt that I just entered 5 characters. But the specific content I just entered becomes encrypted. Just displayed. This is equivalent to, although I now enter this device, but when checking the password, can't see its password. Sometimes on projects, you will inevitably ask others to help you debug the equipment. After logging in, others can help you debug, but he can't check the password. Let's talk about the basic configuration. That is, configure an address. We are still advanced to the global mode. Enter the 00 interface. Then assign an IP. For example, I now configure a 1.1.1.1. But there is a difference. If I configure a 24 here, the representative mask is 24 bits. Can I configure it please? If I configure 24-bit mask, I can only choose 3, 255 and 10. It does not support direct use of Arabic numerals. Dotted decimal only. Press enter. You may find it a bit strange. Logically speaking, this interface is configured with an address. There should be a pop-up window prompting. For example, it will tell me that the interface is already open. But didn't. For Cisco interfaces, although you configure the IP, by default it still doesn't work. You have to open it manually. The command to open manually is called no shutdown. Wait a minute and it will pop some logs out. It will tell you. Now the 00 interface switches state to up. Changed state to up. The 00 interface has started to work normally. We can check it out. Let's look at the interface on the device. Show IP interface brief. Here we can see the layer 3 interface on the device is now. Look. This is the 00 we just configured. The address we allocated is 1.1.1.1. There is a manual here. Indicates that this is a manual configuration mode. This address is entered manually on the interface. Called manual. Here is an unset. It means that this interface is not configured now. There is a status here. Is the physical state. The protocol on the right is the protocol state. Now both states are double up. For a device. If you want a device's layer 3 interface to work. That is, let this interface with configured IP work. Then the state between the two must be double up. In this way, the interface can perform data forwarding normally. Finally, let me tell you, if we did not manually shut down the interface just now, it will have a hint here. This is called administrator down. By default, they are all down. Sometimes everyone will find a state. That is, the physical state is up, but the protocol status is down. There is such a possibility. The physical state is that the interface only needs to be plugged in with a network cable. This port light is on. It means up. But the protocol status is not necessarily up. That is, a transmission medium is connected to both sides of the interface. Some parameters may need to be negotiated in the middle. If the protocols encapsulated on both sides are different, then the protocol status of the interface is also down. Also does not work properly. Here are some corresponding security issues mentioned. So you sometimes see down here. If the interfaces are up and down one by one, this interface cannot forward data. There is no way to forward business traffic normally. It just doesn't work. We just configured an IP address for the interface. 1.1.1.1. Then it worked. Here is a simple test. Called ping. Let's ping 1.1.1.1 now. Press enter. We send a message out here. In the whole EVE. If on a Cisco device. We use a network device to ping an address. An exclamation mark means pass. But if on a virtual PC, it is not an exclamation mark when it sends a message. For example, I am now pinging another address. Ping 1.1.1.2. That for the environment. No .2. I now only configure an address for its interface. The peer is not configured. So it stands to reason. If I go to ping an address on R1, it sure doesn't work. A full stop means no. I hope that when you work in the future, I see exclamation marks. Today we will also talk about ICMP. This ping uses. It is the encapsulation of packets such as ICMP. The above mentioned is the basic operation of the equipment. Next I will talk about some new knowledge. The last lesson was about IP addresses. There is a core knowledge point. I don't know if you still remember. Communication on the same network segment can be directly communicated. Cross-network communication is not allowed to communicate directly. So first let me tell you. There is no problem with this sentence. We will do a verification today. Can they pass? How to get through? This will involve a protocol we are going to talk about today. Called the ARP protocol. Let's not talk about cross-network segment communication. This is too deep. Let's study the same network segment first. So I'm going to ask you a very basic question now. Suppose now there are two PCs. I would like to ask the students how to judge whether they are in a network segment. For example, I now configure an address for the left. 192.168.1.1. 25-bit mask. The address configured on the right is 192.168.1.2. 26-bit mask. Okay. Can they be pinged? Look at this sentence. Communication on the same network segment can be directly communicated. Cross-network communication is not allowed to communicate directly. This is a forwarding principle. There is nothing wrong with this sentence. But when real data communication, is this sentence so absolute? We directly test out the truth. Let's see if it works. Okay. Then these two devices will be deleted. Because we won't be using them later. Just for an experiment. We add two PCs. We can write 2 here. Connect the lines after adding. It's all the same steps. Then pull it away. Pull it out clearly. Now turn on the device. We are going to configure an address for it. The configuration inside the PC is very simple. Click to open it. After opening it is like this configuration format. It also requires you to control the PC through the command line. We will now configure it according to this address. On the left is 192.168.1.1. 25-bit mask. On the right is 192.168.1.2. 26-bit mask. So we just type IP 192.168.1.1. Notice. Mask on PC. It can support the configuration of the input mask. Let's configure it. It is now configured. 192.168.1.1. The mask is 255.255.255.128. Okay. We go to PC2. IP 192.168.1.226. Configured. 192.168.1.2. The mask is 255.255.255.192. PC1 is 1.1. Is 128. PC2 is 1.2. Is 192. It is true that the two of them do not seem to be on the same network segment. Let's ping to see if they can pass. Look. They pass. Isn't that a bit weird? Why it works? We said before that communication on the same network segment can communicate directly. Communication across network segments cannot communicate directly. They must be across subnets now. The masks are 25 and 26 bits respectively. It's definitely not consistent. The same network bit is called the same network segment. Network bit match. Each corresponding must also be consistent. Now let me give you a concept. We say that communication on the same network segment can communicate directly. This same network segment is not the same network segment as we think. But for devices, PC1 thinks that PC2 and it are in the same network segment. PC2 thinks that PC1 and it are in the same network segment. They can communicate between the two. Whether they are on the same network segment or not, we don't know. When PC1 goes to ping the 1.2 address of PC2, it doesn't know that the mask of PC2 is 26 bits. For example, you access the interface of a device, configured an IP. When you ping this interface, it will not suffix its mask. Or, now there are so many servers on the public network. We use all DNS domain name resolution. After you finish parsing, you can't parse to the mask of the peer. That is, when PC1 and PC2 communicate, they don't even know what the other's mask is. So if you don't know the other party's mask during communication, it judges the network segment has a judgment rule. When we communicate, how to measure whether two addresses are in the same network segment. First step. During communication, PC1 is now called the sender. It is sending data externally. The host on the sending end will use its own mask. Add the IP address of the other party for calculation. The result of the operation is the network segment of the peer end. The network address. After calculation, compare the peer network segment with your own network segment. If consistent, then the message will be sent. That is, if they are consistent, they are considered to be on the same network segment. For PC1, if we do the calculation now, what is its address? Let's calculate. 192.168.1.000000001. The mask is 25 bits. Then the mask is 255.255.255.100000000. So am I trying to come up with what I have now? So now to get the network address. The mask is now only these bits, corresponding to the IP network segment, is also the network number. This is the content of the subnet mask mentioned earlier. A subnet mask of 1 corresponds to the network bit. A subnet mask of 0 corresponds to the host bit. Let's not talk about the first 24 bits being 1. It is 192.168.1. Then the latter bit corresponds to 1. This one is sure. That is actually 0. I don't even look at the corresponding ones behind, because the mask is now all host bits. So actually, the network segment I counted is this. The network segment is a 25-bit mask, because the mask of PC1 itself is 25 bits. So this is what PC1 thinks is its own network segment. Next, PC1 will calculate the network segment of the other party. The network segment of the other party is 192.128.1.2. Then 1.2 here is 10. This is called the peer IP address. Then take your own mask to calculate. You will find, when the calculation is over, now own mask is still 1. This bit corresponds to 0. All previous values. That's how it works. The last 7 bits are all 0. Calculated is also 192.168.1.025. This is the network segment of the other party calculated by PC1. Now PC1 thinks they are in the same network segment. Then the data is sent. The data has arrived at the peer. This ping pays attention to back and forth. Send a packet. Send back a packet. That is. Now I want to actually do network communication. Just sending this data packet will not work. Still have to send it back. So before sending it back, PC2 also needs to perform calculations. Calculate whether they are in the same network segment. It is 192.168.1.2. 1.2 is 000000010. This is what PC2 thinks is its own IP address. Its own mask is 255.255.255.110000000. Then the next step is to calculate its own network segment. In fact, these two corresponding network segments, these 2 bits correspond to the determined value, is 0. So the network segment is 192.168.1.0. 26-bit mask. PC2 should now take the other party's IP. Calculated with myself. The other party's IP is 192.168.1.000000001. PC2 thinks that the network segment of the other party is 192.168.1.0. 26-bit mask. Now PC2 receives the data packet sent. See that the address of PC1 is 1.1. It takes its own mask and calculates PC1. Found that they are on the same network segment. PC2 communicates with PC1. In the process, while host A and host B for us, we know they are not on the same network segment. But the device itself does not know what the mask of the other party is. So when they communicate data, what you see is your own mask plus the other party's IP. Calculate the network segment of the other party. So the PC thinks that other PCs are on the same network segment as it. It sends packets to other PCs. Or reply packets. It thinks that it is not on the same network segment. And does not send data packets. Let's do a harder one next. We replace the right side with 192.168.1.5. 30-bit mask. First of all, let's change this to 192.168.1.5. Let's calculate together now. First PC1 and PC2 go to ping. Definitely take your own IP. Own mask. Own network segment. This is no problem. Its own network segment is this. Now take the other party's IP and add your own mask. The other party's IP is 0.5. So it's 0101. Now it thinks that the network segment of the other party is still this. So in fact this packet can be sent out. No problem. Now the packet is sent to PC2. For PC2, its IP, mask, and network segment, there is no problem. Now we have to calculate the following part. Now it is the IP of the other party. Add your own mask. Own mask is 255.255.255.1111100. I feel like I can't get through. Because you may feel that the mask I wrote is too long. IP is 192.168.1.000000101. Now it's time to start calculating. Calculate your network segment. 192.168.1.4. 30-bit mask. So now we have to calculate with the other party. The other party's IP is 192.168.1.000000001. Then the network segment of the other party is 192.1681.0. 30-bit mask. When the calculation is over. Found a problem. PC2 is now 1.4 network segment. PC1 is the 1.0 network segment. They are not in the same network segment. So it stands to reason. PC2 has no way to reply data packets to PC1 now. Let's come to PC1 here. Go to ping the address 1.5 again. Unreasonable. There is a timeout here. Mean timeout. So no ping. That is. The packet was indeed sent. PC1 sends a packet to PC2. Because PC1 thinks that the two are on the same network segment. But PC2 did not reply the packet to PC1. Because PC2 thinks that the two are not in the same network segment. Then everyone will find out. No matter which mask. It does not seem to belong to the three categories of ABC we talked about before. We call a class like ABC the main class. This is defined by the organization IANA. Then these are subnets. We have all subnet. After subnetting, we can indeed divide more network segments. We can make multiple IP addresses in a large network available to others. Divide into different network segments, equivalent to save address. But it creates a new problem. It is how to communicate between different subnets now. So now everyone needs to know a concept. We'll talk about routing in the next lesson. Although we will not talk about routing today. But you also need to know. Because this thing can't be separated. For PC. If the PC now wants to access if it is not in the same network segment as the device, it needs to be routed. That is, access between PCs on the same network segment, without any other equipment, can communicate directly. But if like this 1.1 and 1.5 want to communicate, then there is no way to communicate directly. It needs to have a router. Or a layer 3 switch and firewall that supports routing functions. Communication is by IP packets. Determined by the source IP and destination IP in the header. In the future, intervene in a router. Then this router. It is called the respective gateways of the two PCs now. We will now mention a new concept. These are two PCs. Future. If different network segments communicate. No direct communication. A new device must be interposed. This device is called a router. The two PCs will be connected to the router respectively. After connecting, the IP addresses of the two interfaces on the router will be used as the gateway parameter on the current device. Let's take a look. We open this TCP IP. Tick manual mode here. If my computer wants to go online now, some parameters must be configured. Then the configuration parameter has an IP address. Network card mask. The last parameter is called default gateway. This is for domain name resolution. Let's not look at this. For our daily surfing. Not communicating within the LAN. You need to fill in a parameter called gateway. Let me briefly talk about what is called routing. This is PC. Here is a router. Connect to some public networks outside. When you are online. In fact, all access is to the operator's network. But the problem is, The operator must not be in the same network segment as you. At this time you need to have a device. It to help you access. This device is the current gateway device. Strictly speaking, you connect with it. You belong to an intranet. The interface it connects to you is your gateway. This address must be on the same network segment as yours. If it crosses the network segment with you, you can't access it. It can't help you forward. Your address and this interface address are a network segment. If you access across network segments in the future, you will not go directly to the address across the network segment. Make a direct connection. Instead, find the gateway first. It's here to help you forward. The same is true when the data comes back. Go back to this device first. Then through the corresponding routing function on this device. So the PC will hand over the data to the gateway. The gateway helps itself to forward. So the gateway parameter is very important. For us, the gateway must first know the information of the destination network segment. For example, this PC is now on the 1.0 network segment. The PC on the opposite side is on the 1.4 network segment. If I want to forward data across network segments now, then the router in the middle acts as a gateway. At least it needs to know the information on both ends. So this is a basic logic of it. And a device acting as a gateway like this, it must have the ability to forward across network segments. Send data from one network segment to another network segment. Now I assign an after-school assignment. You can do your own experiments after class. Let me talk about the experimental requirements. If your emulator is not installed, install it early. Okay. I'll draw a picture for you. After class, everyone, do your homework according to the picture I drew. I won't show you in class. Let's talk about it in the next class. These are two PCs. In the middle is a router. The router on the left. Give it an address. For example, 192.168.1.100. 24-bit mask. This is the 1.0 network segment. Suppose the IP address on the right is 192.168.2.100. 24-bit mask. It is the 2.0 network segment. Now these two are cross-network segments. In the middle is a router. Then, for the router, I now assign an address to the left and right sides respectively. The address on the left is 192.168.1.254. 24-bit mask. It is in the same network segment as the PC on the left. The address on the right is 192.168.2.254. 24-bit mask. Set up your own environment after class. Practice the basic configuration. This is the address of both ends. IP will be configured on the host in the future. We just demonstrated configuring IP. Wait a minute and I'll show you how to configure the mask. In addition, the router enters the interface and configures two addresses. No need to do any configuration afterwards. That is, only need to configure IP for the host. Configure IP for the two interfaces of the device. The rest do not need to configure. And see if they work. It doesn't work. That is, if only the address is configured. The two of them are incompatible. I'll leave this to you after class. I won't show you in class. Let's move on. For routers, two interfaces are configured with IP. This IP address must be on the same network segment as the PC. In this picture, the router device acts as a gateway in the whole graph now. Then the meaning of the gateway is, data access across network segments requires a gateway. It is equivalent to a certain PC is a 2.0 network segment. It can only communicate with the data of the 2.0 network segment. If a switch is connected here, many devices are connected to the 2.0 network segment. PC can communicate with them. But if the 2.0 network segment wants to communicate with the 1.0 network segment, then it is impossible to communicate directly. Just go to the gateway first. Then the gateway is configured in the internet directly connected to the PC. The address of this interface. The PC is going to find this address. Pass the packet to it. It comes to help me retweet. It is equivalent to providing forwarding capabilities across network segments. The gateway is configured under the interface of the router, or under the VLAN if interface of the layer 3 switch. It is also configurable when communicating later. The PC will take the IP of its own network segment. That is the mask. Add the IP of the other party for calculation. If it is calculated that the network segment of the other party is in the same network segment as yourself, it directly finds the device on the same network segment to communicate. If not in a network segment, PC will find its gateway. Let the gateway help it communicate. So it is equivalent to realizing forwarding across network segments. Okay. Now we are officially learning ARP. Now there are several problems in the whole picture. First question. How did the PC find the gateway? Second question. How does the gateway send data from network segment 1.0 to network segment 2.0? This is at the routing level. When we talk about routing, we will talk about. Secondly, for data encapsulation. We all know the 7-layer reference model. Each layer must be encapsulated. Then PC1 sends data to PC2. No matter what happens on the upper floor. If you are doing 2-layer encapsulation, how are the source MAC and destination MAC packaged? Actually, this will involve the knowledge we are going to talk about today, called ARP. Okay. For 2 devices, we first reconfigure it with an address 1.1.1.1 24-bit mask. The device on the right is the same. We first configure a network segment 1.1.1.2 24-bit mask. Then, let's capture packets here. When you install this, Wireshark will also be installed together. It's a software for dummies. Very simple. Open Wireshark. This is a software that captures packets. In the future, when 2 data communicate, need interactive message, PC1 has to send data packets out of this interface. When PC2 replies to the packet, packets must be sent out from this interface. Packet forwarding. Then all data flowing through this interface in the future. If you capture packets on this interface again, can be captured. For this interface, no data yet. So no data has been captured yet. When we encapsulate data, I want to ask you a question. I draw a simple diagram here. For example, 2 PCs communicate. 1.1.1.1 24-bit mask. Communicate with this 1.1.1.2. Then to package. Let's not talk about the upper. Let's look at the second and third floors. Suppose this is a 3-layer encapsulation. The front is a 2-layer encapsulation. We will also talk about the process of data packet forwarding today. Let's start now. For 3 layers, we are blocking the source IP and destination IP. Access destination IP address from source IP address. That is, from 1.1.1.1 to visit 1.1.1.2. So how do you know? Are you going to visit 1.1.1.2? This thing is very simple. Future. When you access data. Now the application layer generates a data seal layer by layer to the network layer here. How do you know the IP of the peer? When we go to ping. In fact, ping is suffixed with the other party's IP. Data encapsulation. Now ping this is effectively equivalent to specifying the. It will populate this field. If you visit some services on the public network. For example, you visit Google. Then it's all based on. Now the DNS on the device will help you complete the domain name resolution. You are in the corresponding application. When visiting the corresponding address, it will automatically fill in here. So, we don't need to care about the destination IP. We can generally perceive based on the upper layer. That is, transport layer or application layer. We don't care about the 3-layer encapsulation. Let's take a look at the second floor. For the second floor, we must have source MAC and destination MAC. So let's say my source MAC is AA. My target MAC is BB. Then the source MAC AA is already known. But the question is, how can we know the destination MAC? For 3 layers. I can ping its IP. But we're not going to ping a MAC. If I don't know the destination MAC, I can't do data encapsulation now. Just can't ping. So now we need to get this parameter. We're going to make an inquiry. So it is necessary to use the ARP protocol to achieve. This protocol is called Address Resolution Protocol. It's simple. In one sentence, it is known IP to find MAC. Now we know the IP address. 1.1.1.2. Now ask for the MAC address it corresponds to. This is ARP. Now I know the IP of the peer. Hope to get the corresponding MAC address. So to make the corresponding data request. Then please note. Before future requests to the destination MAC address, real data cannot be sent. Like now. Here we are. It is the captured data packet under the right interface of the PC. I'm going to ping PC2 now. That is, ping 1.1.1.2. For now. After the ping is sent out, the data can be captured here. Then when the data is captured as a whole, we'll look at a parameter. Now PC1 sends data to PC2. The content of the data in PC1 is a broadcast encapsulation via ARP. Encapsulated is an ARP packet. Now the problem is, who has 1.1.1.2? I sent a ping. Ping actually uses the packet encapsulation of the ICMP protocol. But you will find, before the ping succeeds, an ARP is sent first. After sending ARP, this thing returned the packet back to it. 1.1.1.2 is at. Behind this is a MAC address. That is, 1.1.1.2 is on the MAC address next to it. This is PC2. Everyone must first know. When we communicate data as a whole, before A sends real data to B, it must first be able to encapsulate the MAC address. Then before encapsulation is complete, they cannot communicate normally. What is encapsulated here is an IP. But everyone should know. Up to the IP is the 4th layer. TCP and UDP. Further up is the data encapsulated by the application layer. But because the encapsulation cannot be completed here on the second floor, so now it is impossible to forward data normally. Then what we have to learn about ARP? It's actually another message. Everyone should know this. In the ARP packet, and no other headers above, it has only 2 floors. Above the second layer is an ARP layer. For ARP, We usually say it is a layer 2.5 protocol. That is, this is our second floor. Generally speaking, is E2. Such a packet encapsulation. There will be 4 contents in ARP. The first one is called sender IP and sender MAC. That is, for the current data, to mark the MAC address. Further down there is a target IP and target MAC. Now PC1 is going to ping PC2. But it doesn't know about PC2's MAC. It will send an ARP packet to ask. Sender IP is PC1 itself. 1.1.1.1. Sender MAC is AA. Target IP is 1.1.1.2. Then what is the target MAC? How do you think this packet should be sent? PC1 now wants to send a data packet to the other party. That is, send a packet to the device with the address 1.2. But don't know where it is. If you send it, you must encapsulate the destination MAC. But I can't get the target MAC. Now is there any way to make the data packet of PC1 send to the device of PC2? In the data encapsulation of each layer, there is a thing on the second floor called broadcasting. I will give you a simple example. Multiple devices may be connected to a switch. For example, it connects multiple PCs. This is PC1, PC2, PC3, PC4. PC1 wants to communicate with PC4. That now requires 4 MACs. But since PC1 doesn't know where PC4 is, there is no way to send data packets to PC4 alone. So now you can try to send a message. As long as this message is forwarded by the switch, let all devices receive. It's okay. This method is called broadcasting. So now you can take advantage of this form of broadcasting. Send a message. Let other devices receive. When PC4 is received now, as long as now it sees that the destination MAC is itself, the IP requested by PC1 is also itself. It will know that this packet is sent to itself. It will respond that PC1 corresponds to its own MAC. For example, PC4's MAC is DD. For now, a packet is sent to ask the destination MAC. Although there are only 2 devices in the environment. Now this packet is on BB. That is, arrived at 1.1.1.2. Received this packet now. It is a broadcast. Then please pay attention. The second layer is a total of 48 bits. The MAC address is all 1. Reflected in the message. We now use hexadecimal to represent. Actually 12 Fs. We call it all F. This is a broadcast. This is enough for everyone to understand. Now this ARP packet is sent from PC1. Sent to the device PC2. After PC2 receives. See that it is now a MAC address like AA. Sent it a message. It requests its own MAC. So since this broadcast now, just as a means for PC2 to receive the data, then PC2 will reply its MAC. So for PC2, it will now make a reply to the overall data. Let's complete the second floor just now. In the second floor, we are now encapsulating. Please pay attention. The target MAC is all F. Then here is all 0. All 0 means unknown. The message we are sending now is a broadcast message. So our target MAC here is all F. We sent target MAC in the future. It is all 0. Represents an unknown. Now this is what the message looks like. This is the message sent by PC1. PC2 now needs to target the message just sent. Make a reply. When replying, the source MAC and the destination MAC must be swapped. Surely we don't call swapping here. But now the source MAC must be yourself. But the destination MAC can be filled in. PC1's MAC is up. Because in the data packet sent by PC1 to PC2 indicates that PC1 is now AA. The source MAC in the data sent by PC1 is AA. PC2 knows that PC1 is now AA. When sending, PC2 regards BB as the source MAC. Reply to PC1. Then for sender IP and sender MAC. About to make changes. Sender IP and target IP. They are reversed. Equivalent to this is the data packet sent by PC2. Sent to PC1. Sender MAC is the MAC of PC2. Is BB. We fill in here. Then target MAC is not unknown at this time. This is directed to PC1. PC1 is now going to send data to PC2. Logically speaking, the 4 layers should be directly 3 floors. And layer 2 are both encapsulated. This is data encapsulation. 4 layers sealed no problem. 3 layers sealed no problem. When sealed to the second floor, found that the destination MAC does not know where. Therefore, the second layer cannot be encapsulated. But at this point a problem arises. If you don't encapsulate the second layer, then this data cannot be sent. If it is not encapsulated, it does not conform to the overall TCP/IP. We talked about 2 encapsulation standards for data link layer. One is E2. One is 802.3. But now the most used is E2. That is to say, under the encapsulation standard in the second layer, we want to encapsulate the source MAC and destination MAC. It is the name of an encapsulation standard, not a special parameter. Okay. Let's summarize the process. Since the second layer cannot be encapsulated now, as a result, this message cannot be sent out. So you definitely need to ask the other party's MAC to send. This is known IP seeking MAC. Now we have to give up the original data encapsulation. Instead, the ARP packet is encapsulated first. For ARP, it is a message encapsulated in the data link layer. But there is no other layer on top of it. This packet is small. Then in the ARP sent now, there will be a sender IP in its field. Its MAC is PC1. Target IP MAC is PC2. Now for PC1. It does not know target MAC. Because it doesn't know the target MAC of PC2 now. So this position is all 0. Represents unknown. Then the MAC in the second layer sent by PC1 knows. The target MAC is all F. Indicates that this is a broadcast message. Send this broadcast message. PC2 in the final environment can definitely receive the broadcast packet, because it is obliged to process and receive. The first thing to do is to disassemble the message. It will be disassembled from the bottom up. First remove the second floor. It has been dismantled. After dismantling the second floor, it was found. The second floor is all F. This is what was sent. When the message is sent with all F, it will be processed. Source MAC is AA. PC1 knows that AA is sending data packets to it. The packet sent by AA to PC1 is. I would like to ask. What is the MAC address corresponding to the PC1 address? Then PC1 will reply to it. It will start to complete the package locally. Then when packaging, sender IP is itself. Sender MAC is also itself. Target IP and target MAC are each other. Because when the other party sent a data packet to PC1 just now, wrote my own source MAC. So PC1 knows it's the other party's. So reply with unicast. Send data to it 1-to-1. We call it unicast. This is ARP packet encapsulation. Then seal the second floor. The source MAC of the second layer is itself. Is BB. The destination MAC is AA. These are already known information. The data comes back. When PC1 receives the message from the other party, it will be recorded locally. Now the MAC address corresponding to 1.1.1.2 is BB. It will be recorded in the local ARP cache. Please pay attention. There is something called ARP cache locally. This cache will record a corresponding relationship. 1.1.1.2 The MAC address corresponding to such an address is BB. This will be recorded in the ARP cache table. Then it is equivalent to filling a content in this table. Then once the table has this content in the future, before sending data, it will not know whether the second layer should be encapsulated. The real process is like this. When PC1 now wants to send a data to PC2, PC1 checks to see if there is such a cache in the ARP cache. If PC1 wants to send data to 1.2, know that it corresponds to BB. PC1 starts packaging directly. If PC1 is going to send data to it now, first look at your watch. No such entry. Then send an ARP packet to request. After the request, there is this item locally. Then perform the following data encapsulation. Is such a process. In order to make it easier for everyone to understand, I said it was because it was sealed to the second floor. I don't know how it was sealed. It's just our way of saying. For equipment, it will first look at the cache. If there is no cache, just request. After request, when the record is encapsulated in the local cache, now PC1 knows that 1.1.1.2 corresponds to BB. It will be packaged directly. If the table is checked and the table does not, it sends ARP. Then I just mentioned a word called broadcasting. I feel that everyone is on the word. Might not be very good. Talk to you again. As a broadcast message. The range it can transmit is called broadcasting. We will come into contact with the switch in the future. All interfaces of the switch. By default you do not do redundant configuration. It's all a broadcast domain. A broadcast domain means the picture I drew for you just now. Multiple devices connected to one switch. It's all PCs one by one. If now it is connected like this, in the middle is a switch. Then PC1 sends a broadcast packet. They can all receive, because they are in the same broadcast domain. This is called broadcast domain. It is the delivery range of broadcast packets. We just mentioned another device called a router. It's not the same as a switch. For routers, each of its interfaces is a broadcast domain. That is to say, a broadcast data packet cannot be sent to the router. This is the delivery range of a broadcast packet. We also refer to a broadcast packet that is sent. If there are multiple devices in an environment, PC1 sends a data packet. Since PC1 is now a broadcast, all devices can receive. If as a receiver, a device receives a, but not for it, will it reply then? Look. Now PC2 requests 1.1.1.2. If there is a device that is 1.1.1.3, it also received this broadcast. So will it handle it? If this device finds, now the target IP requested by PC2 is not it, then it just doesn't want this packet. Only the request is the real target IP. It will reply when the data passed. Because I don't know the other party's MAC. A broadcast is sent when the data comes back. Since the receiving end can see the MAC address of the sending end, so it is able to know Now the MAC corresponding to 1.1.1.1 is AA. So in fact its local cache table. It will be updated to 1.1 corresponding to AA. Direct address encapsulation. Then sent it. This is its flow. Some students will ask. If the switch knows the corresponding MAC, will respond to ARP. Is this the ARP proxy? No. We'll talk about ARP proxies later. ARP proxy refers to if the devices at both ends think they are on the same network segment, will directly request the other party's MAC. But sometimes you find, although they are on the same network segment, but sometimes a router may be connected in the middle. They are indeed on the same network segment, but not under a broadcast domain. This is a rather special scene. In ARP proxy, it will involve whether the middle is the same network segment, and a broadcast domain problem. So, the switch knows that the corresponding MAC responds to ARP is the ARP proxy. This statement is wrong. In addition, the switch knows the corresponding MAC does not refer to the MAC address table of the switch. Nothing to do with it. It will not reply to ARP proxy unless the routing function is enabled for this switch, and the ARP proxy is enabled on the interface. Generally speaking, only the router interface of the Cisco device. By default it has this function. Generally, we will not use the switch as an intermediate device. So, here are some differences between them.